All right, in section 5.3, we're going to look at what's called the definite integral. And so far we've done the indefinite integral, which is just finding the general antiderivative. Okay. We did an example in a previous section where we plugged a few numbers in after. We were actually computing a definite integral. We just didn't really acknowledge it at the time. But this whole course we've been asking questions like how much is something changing during the second hour? And if I knew mass, then we know we would just plug 2 in, subtract the mass at 1, and we'd get our result. The difference now is I'm starting with a rate of change. So what we'll do is we'll anti-differentiate and then plug the values in. This is what's called a definite integral, and there's notation for this. The definite integral from 1 to 2 of your derivative here is evaluated by finding m of 2 minus m of 1, where m is the antiderivative of m prime. And this is what's summarized and wrapped into the most important theorem of calculus called the fundamental theorem of calculus, where if you have capital F being the antiderivative of some function little f, then you evaluate the definite integral by computing the antiderivative and evaluating it at the upper limit, that's what we call b, and then the lower limit, which we call a. And there will be an in-between step here. You'll see it on the first couple examples. You'll see it on every example, where we find the general antiderivative, and we use this evaluation bar. We saw it show up when we were doing differentiation, but we didn't use it a ton back then. So this just means this, okay? But that step will come before this step. So you'll see with the first few examples, and you'll catch on pretty quick. So we still have to compute antiderivatives. That's the hard part of the problem. The definite integral just goes one step farther, and we plug some numbers in. So let's go through some examples. There. Okay, so according to the fundamental theorem, we deal with this by finding the general antiderivative first. That would be 5t minus t squared plus some constant. Hopefully you're still remembering to include that constant. Usually you finally remember to include it, and then you're going to see it vanish here. So we evaluate this from 1 to 4. So we just call that vertical bar an evaluation bar. Okay, so the general antiderivative first. So you're still doing the previous few sections to do these problems. What the fundamental theorem says is now go farther and plug in your values. So we'd have 5 times 4 minus 4 squared plus c. Then we plug in the lower value. So it's the top one minus the bottom one. And we have 5 times 1 minus 1 squared plus c. Now you've spent the last few, basically the last week, trying to remember to include the c's here. And what you notice is because I have subtraction, the c's are going to subtract away with a definite integral. And that will always happen with a definite integral. I'll write it down the first few times and then we'll start omitting it. So if we clean everything up here, we have 20 minus 16 is 4. Over here we have 4 and we're subtracting. Everything subtracts away in this problem and we end up with just 0. And that's it. So that's what's called the fundamental theorem of calculus, or at least the application of it. Let's look at B here. Now what should I do with this? This doesn't look like any of our formulas, so we know we're going to do a prep step and rewrite this as the integral from 1 to 9 of x to the 1/2 minus 4x to the negative 1/2. Now we're set up to actually evaluate things. So if we anti-differentiate, we know we add 1 to the exponent, so my new exponent here is 3/2, and then we multiply by the reciprocal in front. We have minus 4. We're going to add 1 to the negative 1/2 here, which will give us x to the positive 1/2. And we multiply by the reciprocal of our new exponent. I'm going to put the c in one more time, just so you're sure that it does go away here. And then we evaluate this from 1 to 9. So after you've taken the general antiderivative, the integral symbol switches to this evaluation bar. Okay, now we just plug things in. So this will be 2/3 times 9 to the 3/2. Remember, that's just a square root of 9 and then cubed. We have minus, I'll go ahead and clean that up. We'll put an 8 there. 9 to the 1/2 plus c minus, now we subtract away this thing evaluated at 1, which would be 2/3 times 1 to the 3/2 minus 8 times 1 to the 1/2 plus c. So you can see again here that our c's are going to subtract away. So because of that, when we do definite integrals, we tend not to write the plus c. But you have to remember to include it for indefinite integrals. So all we need to do now is clean everything up. These 2's down here are just taking roots. So if we compute everything here, I got 4/3. And that's it. So we're finding the general antiderivative, and then we're plugging in a few values. So one thing to note here is that definite integrals give a numerical answer. Okay, we're not getting functions. The indefinite integral give a family of functions. Oops, I didn't scroll down far enough. There we go. So definite integrals, we get a number for an answer because we're plugging things in at the end. And indefinite integrals, we're getting family of functions. And we're sort of doing both, and when we do a definite integral, we're finding a general antiderivative first. Then we plug some things in. So definite integral is numerical, indefinite has that constant tacked on. Okay, I put a few properties down here at the bottom. A few of them should look pretty familiar. The first one looks like this is just our constant multiple rule. So it worked for indefinite integrals. It works for definite ones as well, so you can pull constants out. Likewise, we have our sum rule, so I can break this into two pieces and evaluate them separately if needed. This first one here seems a little strange, but if you were to evaluate the antiderivative, plug a in and then plug a in, you would get f of a minus f of a, which would be 0. So that seems reasonable. If there's no width along the axis, you'll get 0. This one is a little strange. We're always considering ourselves to be going from left to right, from A to B. If you had an integral set up, and you'd never do this on purpose, it would happen, and you'll see it could happen with substitution. You can't apply the fundamental theorem from right to left. You always have to go left to right along the axis. So the fix is you flip the limits so that they're in the correct position, and you multiply the integral by a negative sign. This could occur in substitution. So not a big deal yet, but there are times when that could show up. Okay, so on the next page, we're going to look at a slight restatement of the fundamental theorem of calculus. It's still the same theorem, but it is helpful for application problems. It's actually the way we use the theorem for that mass problem at the top of the page. Okay, on to page 13.